Okay, there we go. All right, it seems like a lot of times when people come back from break, they've forgotten everything, including their name. So we probably ought to review just a little bit. Now, we've talked about the beginnings of ossification. I think we talked about intramembranous ossification last time. Remember that one? All right, and of course, it means, of course, forming bone within a membrane, literally. Well, where does the membrane come from? What kind of tissue gives us rise to that? Mesenchyme, correct. And remember, the mesenchyme is that embryonic connective tissue that really has the potential to become just about any kind of connective tissue. All right, so that gets laid down around the areas where the bones are to form. And what bones are typically formed by intramembranous ossification? Ones of the skull, right? So if I ask you to name a specific bone, what would you tell me? Just give me one. Occipital bone, sure, that'd be one. There's lots of examples because there's lots of bones in the skull. Now, another one, the clavicles, remember those also form with that intramembranous ossification. So the mesenchyme gets deposited at the end of blood vessels around where the bones are to form, so like around the brain. All right, and then centers of ossification develop within it when some of those mesenchyme cells differentiate into osteoblasts. And so we get these clusters of osteoblasts scattered throughout this mesenchyme membrane. Well, as they form, they start to lay down collagen fibers, networks of collagen fibers, and then they deposit calcified matrix, you know, the calcium hydroxyapatite and calcium carbonate. So ossification starts, surrounds the cells. When you surround these osteoblasts with a calcified matrix, they transform into what? What's the mature bone cells called? Osteocytes, right? And so these ossification areas tend to enlarge and merge into these trabeculae of spongy bones. So we've got trabeculae forming throughout really that membrane. And then the surface area of the membrane, some of those cells will become fibroblasts that lay down collagen fibers and begin to form a periosteum, all right? And then, of course, blood vessels are going to invade the periosteum along with nerves and so on. And then the very surface areas of that developing bone get remodeled into thin sheets of compact bone. So we've got then, like on the very outside, there's a periosteum, there's a very thin layer of compact bone, there's spongy bone, and then we have another thin layer of compact bone, and then the other layer, the periosteum. So it's all sandwiched together. And in the open spaces between those trabeculae of spongy bone, that fills in with what? Red marrow, right. And of course, what is the big function of red marrow? Probably a couple things we could say. You know, one of the things it's going to do is nourish the osteocytes that are in those trabeculae and spongy bone. But what else does red marrow do for us? Very important. Makes blood, right. Remember what the name of the process was? Starts with an H. Hematopoiesis. Yeah, I know, it's hard to remember those syllables, but anyhow, the accents rather. But anyway, it's hematopoiesis. So that's forming blood. All right, so there you go. And flat bones, and the epiphyseal ends of long bones are where that primarily occurs. Well, the other type of ossification is the one we got up on the screen now. And I think we started talking about it, but we probably need to review it too and pick up where we left off. That's endochondrial ossification. Now, virtually all the other bones in the body are going to form by this process. So, name an example of a bone that would be formed by endochondrial ossification. Femur, humerus, right, good, excellent. All right, in fact, lo and behold. I just happen to have a femur with me. All right, now, that would form by way of endochondral ossification. What does it mean? It just means replacement of bone, or it's bone replacing cartilage. We'll get it out eventually. Bone replacing cartilage. So the first thing that happens, remember, is the laying down of a cartilaginous model. And I think we mentioned that the last time, right? Well, what is a cartilage model? Well, it's a piece of hyaline cartilage that is in the proper location and has the shape and the proportional size for the bone will eventually go there. Now, where did the cartilage come from, I wonder? I heard somebody whisper it. Speak louder. Mesenchyme, exactly. All right, mesenchyme. So mesenchyme would have migrated into those areas where the bone needs to go, and some of the cells would have developed into chondrocytes, which would have then secreted the matrix that surrounds them. And there would have probably been some of the mesenchyme on the surface forming a perichondrium, which again is a connective tissue sheet with some blood vessels, a few, not many, in place. And remember now, cartilage, as we know, is an avascular tissue, so there's no direct blood vessels in it. The nutrients get to the chondrocytes by diffusion from blood vessels that are out on the margins or the edge of it, and nutrients through tissue fluid just simply diffuse through that matrix into the cells. Well, what happens, of course, is that a perichondrium starts to develop, and a periosteum starts to develop by a thickening, essentially, of that connective tissue covering near the center of the diaphysis of the bone. All right, because that's where bone will start to form, is in the center, essentially, of the diaphysis. So really just about the middle of the bone is where the bone will actually start forming. And so this membrane in this area gets thicker, more blood vessels start to enter. Some of the cells, and there will be some mesenchyme cells right under that connective tissue periosteum, will become osteoblasts. They will start to form what we call a primary ossification center. And they will start to form bone, only this time it's primarily going to be in the form of compact bone. And it forms like a little thin shell, a little collar, if you will, right around the center of the diaphysis of this developing bone. So bone starts to form here. Now, inside we still have cartilage. But as bone starts to be deposited and more calcified matrix becomes present, it seals away the chondrocytes in the center from their nutrients. And what happens to cells when you take away their nutrients? They die. Exactly. And so now what have you got? Well, you've got this thin covering of contact bone on the outside, but in the center, we've still got just this calcified matrix with a bunch of holes in it, kind of like a Swiss cheese. Well, blood vessels like to grow in the path of least resistance, so they start growing into those holes. And osteoclasts are going to come in and start removing some of this calcified matrix that's in there, and blood vessels penetrate, and we form a medullary cavity, a cavity for marrow. All right, and those blood vessels start to move up and down, in either direction away from that center of the bone. So what else happens? Well, as that occurs, ossification keeps spreading. It spreads from the center out toward the epiphyses. Now, initially, this diaphysis is all that is calcified, the epiphyses are still cartilage. However, eventually, blood vessels are going to penetrate into these epiphyseal ends, and secondary centers of ossification develop there. Now, rather than laying down compact bone in the epiphyseal areas, the secondary ossification centers tend to give rise to primarily spongy bone. And ultimately, what do we end up with? Well, we end up with all the cartilage gone except for two areas. There will still be a cartilaginous line, which we call the epiphyseal plate of cartilage. It's still on the epiphyseal ends of the bone, both ends. That's the growth plate. That's how the bone can grow in length to that epiphyseal growth that we'll get to here in a bit. And there's also a thin layer of cartilage here on the articular surface where it forms a joint with another bone. And that's called, of course, the articular cartilage. That one tends to remain for the rest of your life and take care of it, of course. The epiphyseal plates only hang around for a while. By the time you're age 25 years, they've ossified. So they eventually ossify and turn to bone. And the only cartilage then that's left is just the articular cartilage, unless you wear it away. And if you do, then you're just out of luck, because then you've got osteoarthritis. But anyhow, there you go. All right? And you can actually see on this bone, particularly at this distal end, that line, that ossification line along here, that's where the epiphyseal plate would have been when this was capable of actually growing. So here, you can pass these around and take a look at that again. I think you've seen this once, but it doesn't hurt to see it over and over. All right, there you go.
What did you say about when it was growing? What did you say?
Well, as long as the epiphyseal cartilage is there, the bone keeps growing. What did you find we moved? Did I lay it down somewhere? I know I brought it. This is maddening. No, it's not. Now, I know I packed it up and brought it with me. Now, where did I lay it? The gray remote for them. Well, maybe I didn't. Maybe I'm getting so senile. I left it upstairs. Oh, here it is. It was upside down. Ah, thank heaven for small mercies. All right, so let's take a look at this, and then we've got a diagram that we can look at. All right, now let's see here. All right, and we said, this simply means the bone replacing cartilage is what it means. And so we have the cartilaginous model, and then the blood vessels penetrate the developing periosteum, and we start to get the osteoblast forming the primary ossification center. Where was the primary ossification center? Kind of in the center of the diaphysis, right? And then it'll spread out from there. And as that occurs, the epiphyseal ends remain cartilaginous, so they can continue to grow. All right, and then calcification continues. The cartilage cells die, they leave cavities. The blood vessels then penetrate the cavities. And as that enlarges, as more of the osteoclasts remove that calcified matrix, and narrow cavities start to form. And blood vessels then branch off toward the epiphyseal ends, and blood vessels ultimately into the epiphyses, starting the secondary ossification center, which primarily forms spongy bone in the epiphyses. And then, after that ossification is complete, we're left with the articular cartilage on the ends, and the epiphyseal plate cartilage or growth plate within the bone. And that is responsible for epiphyseal growth or for elongation. And here we have a thing. Let's see if somebody hit the lights back there. I think this will show up better. All right, thanks. All right, let's start off. Here's the cartilaginous model. This is just hyaline cartilage. It'll have a really thin perichondrium covering. All right, so remember, an avascular tissue, nutrients simply diffuse in here to take care of the cells. All right, we start with a developing periosteum. Blood vessels grow into it, more blood vessels actually. And some osteoblasts start to form right beneath the surface, giving us that primary ossification center. And the matrix in here starts to calcify, shutting off the blood supply to the chondrocytes, which then start to die. And more blood vessels then perforate the area in the center. Osteoclasts enter, removing a lot of that old calcified matrix. We get a developing narrow cavity and more compact bones spreading off toward the epiphyses, but the epiphyses themselves still are largely cartilage. And then blood vessels enter those epiphyseal ends, and we have secondary centers of ossification starting to develop. So while we're getting primary compact bone here in the diaphysis, the epiphysis is forming mostly spongy bone. That will continue on until we end up with the epiphyseal cartilage plates and the articular cartilage covering the end of the bone, and then ultimately the epiphyseal plates ossify by the time the individual's 25 years, and sometimes, of course, sooner than that. But eventually that will ossify, and then bones can no longer increase in length. However, they can increase in width. And that's another type of growth, and we need to say a word or two about that. So, if somebody will turn the lights back up, we will chat about the other type of growth. And unfortunately, the slide set that I gave you is not the one that has this in it. Okay, I swear these days it's going to come crashing down. And maybe they'll give us a screen that's easier to manage when it occurs. Don't hold your breath. Okay, now, what's the other way that bone can grow? Well, you don't just want bones getting longer and longer, because if they're weight-bearing bones, what's going to happen to them if all they do is just get longer and they don't increase in diameter? They're not going to bear much weight. So we have to have a way to handle that. And I didn't bring the tape with me. Well. All right. Well, the other way that bones can grow is by what we would call appositional growth. Now, I like to think of it more of depositional. Now, I'll explain why here in a minute. But appositional growth is how bones grow to increase in diameter. And that's very necessary, particularly for, well, not only for weight-bearing bones, but for any of them. All right, so how does this happen? Well, essentially what this is the depositing of new bone on the surface of existing bone. All right, now where's that femur? It's laying around here somewhere, isn't it? Somebody hand me it. I don't have to have the whole thing. Half of it's good enough. All right, now, what's going to happen? Well, we're going to have to take this, which will be very small to start with, obviously, and as it grows and as its diameter increases, new bone is going to get deposited on the outside of this existing bone. And when you go layering more bone on top of this, what's going to happen to the diameter of the bone? It's going to get bigger, right? Okay, and it's going to happen really in two ways. All right, now remember, what is the covering? What is the covering of a bone? It has a periosteum, right? That's the covering. And that covering is primarily collagen fibers and elastic fibers, right? But right beneath that collagen fiber, elastic fiber network, we have what's called an osteogenic layer to the periosteum. And what is that osteogenic layer largely made of? Our old friends, osteoblasts and a few osteoclasts, right? Now what do those osteoblasts do? Create new bone. And they create it right on the surface of what's already here. What's the role of the osteoclasts? Break down and remove old bone. So when we get ready to remodel this surface, they're going to spring into action. We don't need them so much right now. We're more interested right now in creating new bone here on the surface. And as you do, obviously the diameter of the bone is going to increase. Now what about in here in the medullary cavity? Well, I think we're going to have to remove some stuff in here as we add more out here. And so we also get a broadening of the medullary cavity, primarily, again, by the action of medullary cavity enlargement by osteoclasts, removing old bone, and osteoblasts, layering down new bone. All right? So as we're adding more to the outside surface, we're taking away from what's in here. And that is increasing, of course, the yellow narrow there in the center. All right? Now, you don't want to just keep it a 1-for-1, obviously, because you want to keep thickening this collar of compact bone, obviously, as time goes by. But in any event, you don't want it being a solid mass of bone. You've got to have that medullary cavity, because in here, there are a lot of blood vessels that nourish these cells. Okay? All right, so there we go. That's appositional growth. So, appositional growth increases the diameter of the bone. How do you increase the length of the bone? What kind of growth brings that about? Epiphyseal growth, right? Epiphyseal growth is for the elongation of bone. Appositional growth is for increasing the diameter of the bone. Okay? Oh, it's simple, right? And why did I say it's more of a depositional growth? Because it's depositing new bone on top of what's already here. All right, there you go. And then eventually, in both cases, we end up with remodeling. You know, as old cells die, we've got to take them out. What removes them? The osteoclasts. They die, they leave those voids within the matrix, calcified matrix. Well, if you don't have osteocytes there to maintain that matrix, then the bone is going to deteriorate. It becomes brittle and breaks easily. So you want to keep it fresh, so to speak. You want to keep live cells there to help maintain it. So that's where the remodeling business comes in. Now, what about that epiphyseal growth? Well, epiphyseal growth, of course, very much depends on the epiphyseal plate of cartilage. And for that, we need to consider, wrong pointing, wrong direction. We need to consider the epiphyseal plate. And there are 4 zones to it. And they are a zone of reserve cartilage. Well, that's just regular old small chondrocytes embedded in matrix. Thin, The length of the width of it basically remains constant. It serves more as an anchor, if you will, or a joint that joins the epiphysis of the bone and the diaphysis of the bone. All right? You don't have to write all this down because it'll show up in the outlines here in a bit. That reserved cartilage that's nearest the epiphyseal end of the bone. So it doesn't matter whether we're talking about the proximal end or the distal end, it's closest to the epiphysis. Then there's the zone of proliferating cartilage. Now what does the term proliferate mean? What does that mean? Multiply or increase in number. Well, what's happening there? The cells are dividing. But as they divide, they stack on top of each other. Now, what is the effect of stacking new cells on top of old, or putting new ones under the old ones? Kind of moves things up, doesn't it? Jacks them up somewhat. Okay. And then we have a zone of hypertrophic cartilage. Well, what does hypertrophy mean? It means enlargement. Enlargement. Hypertrophic cells are bigger. They're getting bigger. Okay. Well, that also has a jacking up effect, too. All right, now, there's another downside to that. Cells get bigger. They get too big for the britches. They outgrow their nutrient supply. What happens to them when they do that? Yeah, they kind of start dying off. And there's another thing that's going to help them croak, too. The matrix around them starts to calcify. And when you calcify the matrix around cartilage cells, what happens to the cartilage cells? They die. Why? They shut off their nutrients. Starve them to death. Now what do you got? You've got a zone of calcified matrix that is largely devoid of living cells. Just a bunch of holes. That stuff is brittle. It's easy to break. What do you suppose you're going to do with it? Send in the osteoclasts. What are they going to do? Take it away. And what's going to come in next to replace it with bone? Osteoblasts. Well, we've got some pretty pictures here in a bit. All right, zone of reserve cartilage. That's the ones we said it's adjacent to the epiphysis. It's just plain old cartilage. Small chondrocytes embedded in matrix. Remains constant thickness as long as this zone of reserve cartilage is there. It's not for growth, but as we said, it anchors the epiphyseal plate to the diaphysis of the bone. And in fact, there's a term that we can use, remember, called metaphysis. This is located in the metaphysis because that is the area between the epiphysis and the diaphysis. All right, zone of proliferating cartilage. Large chondrocyte, oops, yeah, that's fine, okay. Arrays like a stack of coins. Wait till you see the picture of it. It looks like, I think, kernels of corn on a cob. Because these are increasing in number and they're just stacking up. And there are new chondrocytes produced by cell division. What kind of division, I wonder, would it be? Mitosis or meiosis? I think it's mitosis, right? Why? Yeah, they're somatic cells, right. So how many chromosomes have they got? 46, sure. All right. Now, zone of hypertrophic cartilage.
Can you go back to that last one really quick?
Yes.
It's not in this outline.
Oh, it isn't? Okay. Well, anyhow, I mean, it's just common sense in a sense. I mean, really. All right. Now, well, I didn't put everything in the outline, as you know. All right. These birds hypertrophic, they are enlarging, they're getting big. And that gives us lengthwise expansion along with the number of cells. So as the number of cells increase, and as the cells get bigger, that's going to expand, all right, and push that epiphysis higher and higher. So the bones are getting longer, all right? And there we go. Now, near the diaphyseal end, the cells start to calcify and die off. So now we get to the next area, all we've got is what we call the zone calcified matrix. Virtually no cell is still alive. It's mostly just calcified matrix with a bunch of holes in it. It's brittle, and you've got to get rid of it, and it's removed, of course, by the osteoclast removing it, and then osteoblasts come into the area, right there, and they start laying down new bone. Now, what kind of bone are we primarily making in the epiphyseal end of the bone? Is it largely compact bone or spongy bone? Spongy bone, right. All right, and so there we go. And here's the term metaphysis, just as there to haunt you again, because I know I've used it before. See, I rarely forget these things. Well, anyway, there we go. Now, let's take a look at this. Let's cut the lights back there, if you would. Thank you. All right, now here we have a photograph, and here we have a drawing. Now, I like this. Up there at the very top, the pinky thing at the very top, that I don't like the way they did that, because that's actually supposed to be bone. Doesn't look like it. But here's the zone of reserve cartilage, and it's just regular small chondrocytes embedded in matrix, a thin layer, primarily acts as a joint that joins the epiphysis with the diaphysis. Then we have the zone of proliferating cartilage, increasing in numbers. Notice how they're growing in a stack. Doesn't it look sort of reminiscent of kernels of corn on a cob? I like food images, as you know, so anyway. All right, and then we get to the zone of hypertrophic cartilage, where they're getting bigger, and the matrix is starting to calcify, and the combination of the cells getting too big for the nutrient supply, and the calcification matrix means what happens? They start to die. And these are in various stages of death, shall we say, degeneration. And then we just end up with areas practically devoid of all living cells, with one or two there. That's the zone of calcified matrix. But it's not very strong, it's very brittle, it can break very easily. And so osteoclasts start moving in here, removing it, as osteoblasts start to form and lay down new bone. And primarily they are laying down trabeculae of spongy bone in this epiphyseal end of the bone. Now, let's take a look at this photograph, which is not as high a magnification, obviously. But there at the top, you see the small cells, and then you see what look like stacks of coins. Well, that would be where the proliferation is taking place. And then you have the cells that are hypertrophying or getting bigger. And then the matrix starting to calcify. That dark area, that would be calcified matrix. The cells are dying off. You notice there's not a lot of cells in here. Not as many cell nuclei as there were above. And then here is where the osteoclasts are removing that, and osteoblasts are starting to form new bone. All right, there's a trabecula of new spongy bone. And red marrow then migrating in to the space between the trabeculae and the spongy bone. All right, there you go. All right, so there it is. So as this continues, the epiphysis just keeps moving higher and higher. It's pushed away because it's kind of like these things are down here like jacking up a building. Well, they're jacking up the epiphysis. And the bone is growing in length. Here are a couple of osteoclasts. There are 3 or 4 of them here. And these are rather large phagocytic cells. And what are they doing? They're removing calcified matrix. That's primarily what they do. Well, when you do that, you're removing calcium from bone. Where's the calcium going? Probably into the blood. So anytime we've got increased osteoclast activity, you're going to find that calcium levels in the blood increase. All right? I don't like that diagram, so we'll just go with another tidbit or two. So if you click those back on, thanks. And so the thickness of this epiphyseal plate remains essentially constant as long as it's there. But remember, eventually it goes away. It ossifies. It turns to bone. Once that happens, vertical growth of bone ceases. They're not going to get any longer. They're as long as they're going to be. Bone, however, does continually undergo remodeling, which is just the replacement of old bone. Remember, it's about every 7 years your bones turn over. Okay? Because the old cells die, and then they have to be replaced. Now, this is an X-ray showing the epiphyseal plates that are still active. You can see this band here and here indicating the arrows. And so this would be someone who's obviously not yet 25. They're younger than that. They still have active epiphyseal plates, and their bones can keep elongating as long as that's there. Once those ossify, then those will become dense areas, and you won't see that. Now, some things dealing with bone conditions. All right. Let's chat a little bit about hormonal control of bone growth. All right, first of all, growth hormone. Growth hormone is produced by the anterior pituitary gland. Okay? And it goes out into the blood and circulates, and it targets virtually every cell in the body. And what does it cause them to do? Well, it stimulates growth, and particularly in the bones, it stimulates division of cartilage in that epiphyseal plate. So it's going to stimulate cartilage cells to divide. It can also stimulate appositional bone growth as well. So we have both epiphyseal and appositional growth stimulated. And so, what happens if you get too much? Well, hypersecretion, of course, means an elevated production of growth hormone. Too much growth hormone in the blood. Too much stimulation. If you're looking at children who are still growing, or any individual who still has an active epiphyseal plate of cartilage, they can end up with gigantism. What does that mean? They're abnormally tall. All right, their bones get longer than normal. So they're going to be abnormally tall. All right? Why? Because it really stimulates that epiphyseal growth of bone. And of course, also appositional growth, too, to help support their weight. Now, what about acromegaly? What's that? Well, that is something that develops in adults after ossification of the epiphyseal cartilage plate. Because once that epiphyseal plate of cartilage is ossified, bones can no longer elongate. They can't get longer, but they can get thicker. How do they get thicker? Because in that case, the growth hormone is stimulating the appositional growth. Because really growth hormone does both. You've got epiphyseal growth and you've got appositional growth resulting from growth hormone stimulation. Well, if you can no longer have epiphyseal growth, and you can't, once the epiphyses have ossified, you still can have appositional growth. Bones get thicker. And what do you find? Well, you find, for example, like the fingers get thicker. There's a coarsening of the features, like the frontal bone, the brow ridges get more pronounced. All right, I'll show you a picture here in a minute. All right, that's acromegaly. That is hypersecretion of growth hormone in adults after the epiphyseal cartilage is ossified. If it hasn't, if it's still active, you get bigger, you have gigantism. All right? Now, hyposecretion. What is the prefix hypo? Blood or under, right. A low secretion. Well, that doesn't stimulate as much growth. And what can you end up with? Children who have too little growth hormone can end up with proportional dwarfism. They're too short. All right? There you go. Now you have to be careful because growth hormone is available to treat that. But some people later in life have growth spurts, you know, so you don't want to overdo it on the growth hormone or you might end up with a giant, you know. So, well, because, you know, they may eventually have a growth spurt and then really shoot up. All right. Now, calcitonin. That is a calcium-regulating hormone secreted by the thyroid. Where do you find the thyroid? Right here in your neck. Now, elevated levels of calcitonin, what do? They inhibit osteoclast activity. Inhibit osteoclast activity. What do osteoclasts normally do? Remove bone, right? All right. If they're removing bone, they're removing calcium, right? Okay, but here we're inhibiting that. So there's less erosion of bone. There's less reabsorption of bone. Well, what effect is that likely to have on blood calcium levels then if you're not removing bone? You're causing it to drop because you're keeping the calcium locked up in the bones. All right?
This is not removing it.
This is not removing it. That's right. So the calcium stays locked up in the bones, and blood calcium levels will tend to decline. So lots of calcitonin, low blood calcium. All right? Now it's simple. Now, as you might guess, we have a companion. Parathyroid hormone. Now this one, bless you, is secreted by the parathyroid glands. There are 4 of them. They're little disc-shaped things, and they're embedded in the posterior aspect of the dorsal side, if you will, of the thyroid. And they put out what's called parathyroid hormone. It has the opposite effect of calcitonin. This one stimulates osteoclast activity. Now, what happens there? Well, more osteoclast activity, you're breaking down bone. More bone. What's happening to the calcium? Goes right into the blood. So what happens to blood calcium levels in response to parathyroid hormone release? It goes up. Normally, the 2 hormones balance each other, and that's what keeps blood calcium levels regulated and really held within a fairly narrow range of normal boundaries. But let's say you've got a parathyroid tumor that's putting out too much parathyroid hormone, you might end up with really high levels of calcium, which you don't want because then it starts getting deposited in other areas like your liver. Well, what would be the effect of calcifying liver cells on? Well, you could end up with cirrhosis, yes, but you could also end up with some other things. Yes, ultimately that's it, but what's going to happen to the cells in the meantime? They ossify and they die, that's right. And then you end up with the scarring of cirrhosis, which you don't want either. But anyhow, there you go. All right, vitamin D. Well, that one is for calcium absorption from dietary calcium. Where do we get vitamin D? We make that. We can make that. Where do we get it? Cholesterol, right? Converted into vitamin D. What converts it? Sun, right? For UV radiation. Now, chronic deficiency of vitamin D, you end up with rickets. And this is primarily in children. In adults, it's called osteomalacia. But in either event, what is it? Softening of the bones. Well, what's going to be the effect, particularly on the weight-bearing bones, like this one? Well, they either break or they bend. They become softer, all right? And particularly in children, you can get bowing. I've got a photo of that here to show Now, vitamin C is important for bones as well. Why? Well, vitamin C is necessary for collagen synthesis. Now, how much collagen do you find in bone? Dry weight of bone is about how much collagen? About a third, about 33%. The other 2/3 are essentially the hydroxyapatite and calcium carbonate. All right? Well, if you don't have adequate levels of collagen, you end up with fragile, thin bones that break easily. And a chronic deficiency of vitamin C is called scurvy. All right? What else would you get with scurvy besides thin, fragile, easily break bones? Well, where else do you find collagen? Skin, right. Also, as we'll see when we talk about joints next time, periodontal ligaments that hold your teeth in, collagen fibers. Guess what else happens? Thin skin that breaks easily and bleeds because blood vessels become thin and easily damaged as well without collagen. Your teeth fall out, all that good stuff, all right? You don't want that. Well, that goes along with scurvy as well. All right. How do you fix it? Well, you've got to ensure that you don't have a chronic deficiency of vitamin C. So what's an easy way of getting vitamin C? Citrus things and, lots of fruits and vegetables, peppers, tomatoes, all those things. They're good sources of vitamin C. All right, here we have someone with acromegaly. Now, this is before and this is after. All right, now what do you notice about him? Look at his fingers. What's happening to them? They're getting thick. What about the brow there and that frontal bone? It's getting thick and more pronounced. What is happening here? What hormone is responsible for this? Growth hormone, right? All right. Now, what kind of growth is the bone experiencing as a result of this hypersecretion of growth hormone? Appositional growth. It's getting thicker. Why is it not getting longer? Why doesn't it have to worry about becoming a giant? Well, it's epiphyseal plates ossified, right? His bones can't get longer, but they can get thicker, and they did. Now, probably a pituitary tumor, probably responsible. That'd be one of the causes. All right, even though that can be fixed, this is going to remain. All right, once that's there, it's pretty much there. All right. Now, if somebody doused the lights, we can see the rickets, because this is hard to see. But look at their legs. The bowing. Now, what was the vitamin that's the problem here? Vitamin D deficiency, chronic deficiency. So they're not able to absorb dietary calcium. Now, there also could be an issue where maybe they're not getting adequate calcium levels. That would be a problem too. But the classic cause here is a deficiency of vitamin D, a chronic deficiency of vitamin D. All right, now let's talk about fractures. All right, first one on the list is what we call a comminuted fracture. Well, what's that? Bone is broken into lots of little fragments. It's pretty much shattered. All right? And what are you going to have to do to fix something like this? Gather up the pieces, screw them back together, or put plates in place that will more or less put them back into the shape of the bone. Otherwise, you get a very distorted bone when it heals. All right, pretty bad. We don't want any of these, really. I just think of pain with this because we really have a lot of nerves and bone. It's not dry and dead by any means. The word words. Compound fracture, also known as an open fracture. Well, that's where the bone is actually broken and protrudes through the skin. Open in the sense that it's outside of the body now. Now, bad. Why? Well, whenever you break the skin, let the bone protrude, danger of infection, you're going to get some. And you've got to resolve the infection before the bone can properly heal. And bone infections are hard to resolve. Very slow process. Another one where you're probably going to have things screwed back together again and dealing with the infection too. Compression. Bone is crushed. Well, that's like this osteoporosis model where you can see how in this one, there's very little spongy bone here, it's starting to collapse on itself. You can pass that around, take a look at it. We've seen it before, but it doesn't hurt to look at it again. All right, so that's a compression fracture that's occurring in that case. So the spine is actually compressing.
Is that like a stress fracture?
No, that's more like something else that's coming up. All right, green stick, also called incomplete. Now, it's like taking a twig off of a tree, particularly now if you're starting to grow. And if you start bending it, it breaks on one side, but it doesn't on the other. Now, eventually it will if you bend it enough. But typically it's broken on one side, but it isn't on the opposite side. And it's more common in children because their bones are a little softer, a little more pliable than adults. Impact. Well, here just a fragment is broken off a bone and typically driven into another part. There you go. Simple. Well, that's just where it's clean breaking too. All right, that's the most common kind, probably. When somebody falls off, like my brother did, off his pony and broke his arm. But anyhow, and then spinal. Here we go. Now this is where it's twisted, and usually has little hairline cracks with that. Okay, we'll see some pics of these here in a bit. All right, so let's take a look at some films. I'll cut the lights a bit on this one. I think maybe we'll just cut it in half. It'll be enough. Okay, let's see. All right. Can you get it? Okay. All right, comminuted. Now remember what happens here. It's shadowed. So here's a drawing to help you get some sense out of it. A lot of little pieces. And over here, thing hasn't yet been repaired. Interesting. A lot of little bits and pieces. And to fix that, lots of plates, screws, all that stuff needs to go in there. And here is compound. There's a bit of bone sticking out there. Rather messy, to say the least. Again, probably some screwing and plates and things like that to get it back together. Here's a compression. This is the osteoporosis. Look at this vertebra. See how thin it is from compression. And you can see varying degrees of it on these others. Now, that red arrow is showing the compression fracture where it's collapsing. This is a treatment that was tried. It really was not that successful. That is done by injecting ground up cadaver bone into the bone to try to stimulate bone growth. And it does work in some areas of the body. But it didn't seem to work well with osteoporosis. So while it was tried, it sounded like a good idea. It really wasn't all that successful. But anyway, green stick. Now, I don't know how well this shows up. You see the break here, but it's not broken there. Bent, and it's broken only on one side, but the opposite side is not broken. Now, what bone is that? It's broken. Look at that. What's that one? That. So what's that one? Ulna. Right. Okay. See the round head on the radius there? Can't miss it. Well, I think the radius is probably all right, but the ulna definitely is broken. All right. Now here's another ulna. This is an impacted fracture. I hate this because it just shows such a tiny little bit a little chip broken off. That's all it is. Still not a pleasant thing to endure. And here's a simple fracture. Now, I don't know how well it shows up, but both of these bones are broken. It's kind of like diagonal there. Nice clean break all the way across. Okay? That's just a simple fracture. All right. And then here's the spiral. And now this is probably hard to see too. Bone was twisted. You notice a little diagonal hairline crack there? Well, that's it. All right, it's just very, very small. And that would be because of twisting on the bone. And I don't know, somehow it just seems, yes, enough to be with shakes. All right, so there it is. Now, how do we heal these things? How do you go about healing fractured bone? Well, now, the usual cast of characters, some of which are up here and I'm erasing at the moment, are going to play a big role in this process. All right, first of all, one of the things that we need to have is that covering on the bone. What's that thing called? Yep. All right, we're going to have periosteum. Now, if it was broken, if it were disrupted, that's going to have to start growing back as well. Now, remember now what it is. Well, it's mostly collagen fibers and elastic fibers, and then you've got also the blood vessels in there as well. All right, so we have to reestablish a periosteum if it was damaged, and we hope that it wasn't. All right, so then we end up with bleeding into the area, because remember now, blood is highly vascular, bone is highly vascularized, so you're going to get bleeding, and the bleeding is going to lead to the formation of a clot. All right, so a clot forms. So we basically have a clot forming between the two broken ends of the bone.
You said this is how the bone fixes it?
Yes. All right, now, what happens with clots? Well, clots become replaced with what we could call basically scar tissue, which means collagen fibers. Okay? All right, so essentially then, fibroblasts grow into that area as the clot is removed, laying down a network of collagen fibers. So essentially you have a scar between the two broken ends. All right, and then that ends up being replaced with healthy bone tissue. So how are you going to do that? What cells are going to come in and finish the job? Osteoclasts to take out the dead bone. Because remember, when you broke it, you probably killed off the cells, mostly. The osteocytes. So now you've got that calcified matrix that has no cells in it, needs to go. Osteoclasts take it out, and osteoblasts come in and do what? Lay down and form new bone, right? And typically when you do all this, you end up with a callus of bone, where the bone in that area is actually thicker than what was there originally. You know, a callus forms in the sense that there's actually more bone put down than what was over there originally. It's kind of a way of ensuring that it won't break again in that spot. And that remains for a very long time, years. I mean, you can find healed fractures showing up on x-rays years after the fact. Okay? Now, eventually, with remodeling, that might disappear, but it's going to take quite some time. All right, so there you go. Now, that's simple enough, isn't it? Yes. Well, just long enough to remind you, next time it's joints, and we may get started on the brain, so watch the webpage. And there's that chart you got on joints. Print it off and bring it with you. We'll talk about that, yes ma'am.
No, I can't,
Yeah, probably our brain and stuff too. Probably about the middle of April for the next test. Well, that's exam 3 and then final payment, so I think this counting this week we have 5 weeks. Don't worry, I'll fill